What is a probability distribution? Man, probability distributions have got to be one of the most difficult concepts to grasp at first because of all the different structures and meanings these two words can imply. Today, I will give you the main intuition of probability distributions and help you understand this fully before diving into the more complex topics. First of all, what is probability? Probability measures uncertainty. If you flip a normal fair coin, you cannot know if the coin will land heads or tails. If you roll a normal fair dice, you cannot know if you will get a 1 or a 6. Unless you have some crazy foreshadowing powers, you will not know what you are going to get. That being said, how exactly are we supposed to measure probability? The most straightforward way statisticians came up with is to look at all the possible outcomes via a random variable and then say, okay, I want this specific outcome out of these other outcomes. And then boom, you have measured the uncertainty of this outcome. Now, obviously, measuring probability is not always going to be this straightforward. Due to the sheer complexity of this world, statisticians invented different ways to measure probability, depending on the distribution of the experiment. But what exactly is a distribution? It comes from the word distribute, and that word literally means to divide something into multiple parts and spread them out in some sort of way. In the boring world of statistics, we distribute numbers by spreading them throughout a number line or a table or a function. Now, if you add the word probability to the word distributions, we would be spreading, guess what? Probabilities. So in the most basic language, probability distributions describe how numbers are scattered around. Instead of saying numbers, we say probabilities. And instead of saying scattered around, in statistics, we say distributed or assigned to. And we arrive at the main intuitive definition of probability distributions. If you're still confused, let me show you another perspective. You see this one right here, right? In statistics, there are two rules you need to remember. One, all probabilities of an experiment must be non-negative. And two, all probabilities must add up to 1. If they all add up to 1, then that means we can think of these probabilities as building blocks that are part of 1. These building blocks would be decimals because decimals, when combined together, give you back whole numbers. And these decimals would be between 0 and 1. If I were to scatter these building blocks everywhere, then I am the distribution because I distributed these probabilities all over the place. That is the main intuition behind probability distributions. It quite literally scatters 1 into a bunch of pieces. All right, let's talk about how we get probabilities using this function notation. We all know what a function is, right? It's a machine that takes an input and gives an output. To measure probabilities from experiments, we use this function. There are 3 components to this. 1, what is the name of this function? 2, what exactly is the input? And finally, 3, what exactly are we outputting? You know how in high school maths, we name our functions with a letter? It's exactly the same thing here. The letter we choose here is a capital P to represent the word probability. What about the input and its name? In high school maths, we usually treat everything inside the brackets as our input. That input is also a letter. We choose a specific letter that best represents the situation. And in this situation, we are inputting different outcomes from the experiment via a random variable. Now, I have a video on random variables. Be sure to check it out after this video. But basically, they represent the possible outcomes of an experiment, with each outcome being assigned a specific number. But now, you must be thinking, there are 2 versions of the same letter inside the brackets. There is a capital X and a small x. Which one is the input? This is where everyone starts to get tripped up because we're involving 2 different versions of the same letter here. I like to think of it in a mathematical perspective and treat this little x right here as the input of P. However, if you want the real statistical perspective, the reason we involve 2 variables is to formally say and also remind ourselves that this little x comes from this random variable. It did not come from y, It did not come from Z or W. No, this outcome right here comes from random variable X. At the end of the day, X is also a function. It is supposed to map the raw outcome to a real number, which is why statisticians really treat this input as a formal statement that says the random variable X takes the value little x. For example, let X represent whether you get heads or tails in a coin flip experiment. We know X maps heads to 1 and tails to 0. So if I say capital X is equal to 1, then I, as a statistician, am stating the random variable X takes the value 1. That's it. So the answer to this question, it's basically the desired outcome your random variable can take on. Choose whatever perspective that helps you to understand this better. And finally, the output. This will just be a number between 0 and 1. In plain language, this is your probability. We read this notation as the probability that the random variable X takes on the value little x is blank. Now that you understand how probability distributions are functions, what are the different types of distributions? There are plenty of them. They can all be categorized into discrete or continuous random variables. Discrete random variables include numbers that are countable. Numbers that have gaps in between, like 1, 2, 3, 4, or maybe 24, 28. We say a random variable is discrete if it can assume only a finite number of different values or countably infinite number of distinct values. What about continuous random variables? They are the complete opposite of discrete random variables because they contain an infinite uncountable number of outcomes. We literally do not know how many outcomes there are. They go on forever, and therefore we can't count all of those distinct outcomes. So we say a random variable is continuous if it can take on any values within an interval, because an interval will contain all of those uncountable values. Now, I'm about to blow your mind with this logic right here. Depending on the type of your random variable, you will end up with a different distribution with completely different behaviors. For example, if your experiment is a discrete case with a discrete random variable, you will get a discrete distribution. If you want to calculate probabilities, we will use the probability mass function, or PMF for short. In contrast to that, if your experiment is a continuous case with a continuous random variable, you will get a continuous distribution. If you want to calculate probabilities, use the probability density function, or PDF for short. Now you must be wondering, where does PDF and PMF come from? What even are they? I thought you said we're supposed to use this function. Nuh-uh. The problem with this annoying function is that it works for discrete distributions, but not for continuous. You know why? Because there are an infinite number of outcomes in a continuous distribution. Meaning, if you were to find the probability of just one singular outcome, it would be that outcome divided by the total number of outcomes, which is infinity. And you know what we just say at that point? It's 0. Because in basic calculus, 1 divided by infinity is making that number extremely, extremely small. As that number gets large enough, it becomes 0. And that's the reason why this function kind of splits into two different functions, the PDF function and the PMF function. Just use this function if your experiment is discrete, and this function if it's continuous. That's it. And that's the end of this video. I really intended for you guys to understand the main intuition of this topic. I do plan on diving into more detail in future videos regarding both cases, especially the PDF one, because that one is a bit of a pain to understand. But otherwise, yeah, this is just like a huge overview. So yeah, have a nice day.